More minutes?
Sure, sure.
Yeah, sure. Start whenever you want.
Are you going to introduce me, or should I just go ahead?
It's up to you.
Okay, I'm fine. Yeah. Okay. Hi, everybody. My name's Shane, first of all. And this is an awesome opportunity for me because I'm a PhD student from Canada. And most of the conferences I attend are for research. And this is like, actual stuff is happening here. So it's kind of neat. Yeah, so thanks for welcoming me. My talk is about identifying hotspots in the Postgres build system. Actually, before I start, here's my Twitter handle, and this would be really awesome for me and my future research if you guys could actually take a look at my Twitter handle. I just tweeted out a link, and it's a survey, a developer survey. It'll take maybe 5 minutes of your time to fill out. And it's just about how you interact with build systems and these sorts of things. And it really helped me direct my future work if you could fill that out for us. Anyways, back to the task at hand. So we did some work identifying hotspots in the Postgres build system. And I find it's usually useful for me to take a few minutes to explain what I mean by a build system before I start digging in. Because there's kind of overlapping terms. Everybody thinks something different when I say build system. So if we imagine that this pile of Lego, pile of blocks, is the source code of a software project, and this spaceship is what we want to deliver to our customers, well, the build system is the set of order-dependent instructions that take us from the blocks to the actual spaceship. Or in software terms, it's the make files and configuration scripts, these sorts of things, that describe how source code and tech files, documentation files are translated into deliverables and then packaged. And we've been using build systems, developers have, for quite some time now. Since the 70s, the original make tool came out, and this concept of the developer's work cycle as thinking of the code, thinking of something you want to change, editing the code to implement the change, running the build to integrate the change into the deliverables, and then testing what you've produced. And then you circle back around. But in this model, all builds were thought of as equal. So anytime I ran the build, it was just doing the build step. But in reality, some builds are more equal than other builds. So some builds actually take longer than other ones do. And this recent XKCD comment kind of highlights that, saying that one of the #1 reasons for developers slacking off is the code is compiling. So they're waiting for the build to actually complete. And we've got some quotes from GTK developers who say, you know, the build is abysmally slow and it's preventing them from being able to get their job done. So slow builds are actually impacting people, or that's the impression that we get. So what can people do to address build performance in the wild? So if refactoring is a common technique. So if we imagine that we have a 4-file system, a very simple system made up of 4 C files, and we notice that this particular file, when we change it, takes a while to reintegrate, because first we need to recompile this object file, then re-archive it, and then it gets linked into 2 deliverables. So before refactoring this source tree, 4 commands are triggered when you change util1.c. However, if we look at this graph and we find out that util.c is only ever used in the first deliverable, it's never used in the second one, we can actually refactor this code to look something like this, where now if util.c is changed, only 1 compile command is triggered, and then 1 deliverable is relinked. So now only 2 commands are triggered, and we've shaved our compile time in half. But the question is now, imagine I'm working on a real system that's not 4 files. Where do I focus my effort? Where should I look for gains to refactor? And we thought the most obvious one is look for the files that are the slowest to rebuild. Find the turtles. So we came up with a pretty simple 2-step approach to finding them, to finding the slow files. So first step, we extract the dependency graph from your software system. And the way that we do that, I'll explain in the next slide. The second step is we analyze that graph to find out where the slow files are. So going into each step in a little bit more detail, in the first step, we're constructing the dependency graph. So we use this tool called Macau, which is a tool that will parse a debug trace of a build, and it'll understand recursion as well, and piece together the dependency graph. So what I'm showing here is actually Postgres 9.2.4, which is probably ancient for you guys now, but that's the version that we studied. And this is the dependency graph. So on the outside edges are the source files. So these are the ones that there's no command to generate them. And then as you work closer in, that's where things are getting compiled and linked and these sorts of things. So yeah, we have this tool to build this graph. Now, in that graph, we don't have a cost for an edge yet. So we could look at that graph and just say the cost of recompiling a file is just all of the edges that get triggered. But instead, we decided to do something a little bit more practical and look at how much each edge costs. So how long each compile, each link, and everything costs. So we did 10 clean rebuilds of Postgres and timed each command. And then we take the median of those 10 runs, and that's the cost for each edge. So now we've got a nice way of finding out how much it costs to rebuild a file. So we said, let's try this out. So we picked 3 systems, and we said, let's find the slowly rebuilding files. So before I dive in, here are some characteristics of those big graphs for these systems. At the bottom here, highlighted in yellow, is Postgres 9.2.4. We also looked at glib, and we looked at Qt. And I'm showing in blue the number of edges, the number of nodes. So these are files. So this would be like .c files, .o files, executables, libraries, these sorts of things. And then the red bars are edges or dependencies and the rules that trigger. So you can see we looked at 3 systems with 3 different orders of magnitude of edges. So up here, Qt was the largest. It had over 2.7 million edges in their build dependency graph. Postgres has about 121,000. And then Postgres is the smallest down here. glib had 121,000. So we said, now let's go through each one of the source files so that the nodes on the outside of that big graph that have no in edges, and trace through the graph to see how much it would cost to rebuild each file. And then we plotted graphs that look like this. So on the left-hand side are the C files, on the right-hand side are the header files, and each point on the graph is one file. And we sorted it according to build cost. So the stuff on the far right is the stuff that took longest to recompile. So we saw some interesting things here, like for example, down here is where we would expect most .c files to be, triggering one compile and maybe a couple of links. But there were these jumps in the GTK build where some C files actually triggered several compile commands and several link commands as well. So we dug in and found that they had some code generators there where if you changed that C file, it would end up regenerating some code and then recompiling and linking some stuff. So yeah, there was some interesting stuff there. Here on the header files, you can see there are again steps. Some of these header files were included in the source code generator, which meant that they would trigger the same sort of activity. And as you'd expect, on the y-axis at the top here, C files, if you touch them, tend to rebuild very quickly. Maybe 12 seconds is the top here. Whereas if you're touching header files, you pay a higher price. This is what Postgres looked like, which was much more, I guess, flat, what we'd expect. Touching C files never really took more than 2 seconds to recompile. But we found that if you did touch some of the bad header files, it could take more than 3 minutes to recompile. And when we turned to Qt, this is where we said, oh boy, these guys are in trouble. Because there are some C files that actually took almost 3 minutes to recompile, and there were some header files that took over 2 hours to recompile. So if you're unlucky enough to have to touch one of those, it would take forever to fix whatever you were working on. But in any case, we said, this is great. You know, we can sort this stuff. We can find the files that are really slow to rebuild. All we have to do to find the stuff you should focus on for refactoring is just draw a simple line. I don't want to wait more than 100 seconds for my code to rebuild, so everything above this line, I need to look at refactoring. Or maybe you're more patient than me and you say 150 seconds. Or maybe you're less patient and you say 50 seconds. But either way, all we have to do is draw a line. We said, great, so let's pick an arbitrary line. Something we felt was bad was 90 seconds. We read some books and 90 seconds seems to be how long people say developers are willing to wait. So we sent a list of these header files or C files that took longer than 90 seconds to the glib developer mailing list. And we asked them, of these files, do you think any of them are performance bottlenecks? And we got some scary responses. Somebody said, for all of them, no. None of them are hotspots. We don't care about those files. They're not painful at all. Then we asked them why. He said, because none of these files change that often. So we went back to the drawing board. Originally we said, let's look for the slow files. Maybe it's not the slow files that are the bottlenecks, because they might only rarely change, right? So if they only rarely change, people don't have to pay the price of rebuilding them. So maybe what we should be looking at are the files that change the most often. So we said, okay, how are we going to find the files that change the most often? We turned to the version control system. And we did some simple mining. We just looked at, for example, for each file, the number of changes that had happened. And we assumed that files that changed a lot in the past will continue to change a lot in the future. So then we said, okay, let's build those same graphs, draw a line there. What we found is that many of these files already built very quickly. So we thought, okay, that's not going to work either. So focusing on the files that change the most often also isn't sufficient, because they may already be optimal. There's not much you can do to refactor a file that builds in less than a second. So what we suggest is that instead of trying one or the other, you should focus on both. So we call these files build hotspots. They're the files that rebuild slowly, but also they change frequently, so people have to pay that cost of rebuilding a lot. So we took this two-step approach that we originally had and turned it into a three-step approach. So we added a third step where we took the version control stats that we mined integrated it with the stuff we pulled from the dependency graph to get what we call a quadrant plot. And this is a pretty simple concept. We just take the rebuild cost and the number of changes for each file and plot them against each other on XY grid. So each one of these dots would represent one of the files in your system. And then we split it into quadrants. So based on thresholds that you pick for your project, you say, I'm not willing to wait more than 90 seconds, 100 seconds, 20 minutes, whatever it is. That's your threshold for rebuild cost. And then you pick a threshold for the number of changes. So 10 changes in the past is a lot, or 100 changes in the past is a lot, and that becomes your threshold. And then we just say, focus on this red area. Those are the files that you want to rebuild. Those are the files that you want to refactor first. So we said, great, now we've got a metal detector. Let's go try it out on some open source systems and see what kind of hotspots we detect. So for this, we had to pick some thresholds. Like I mentioned, we had been playing with 90 seconds because we read in some books that that's a pretty good threshold. And we also needed to pick a number of changes for the threshold, and for that we picked the median. So anything that changes more than the median number of changes for a file in your project, we consider that a frequently changing file. So some of the things that we found using quadrant plots for the three systems, the three open source systems that we had been exploring. So about 7% of glib's code base was identified as a hotspot using those thresholds. So about 65 glib files. And some of the things we found are that you don't actually have to refactor all 65. Sometimes they'd all bottleneck into one place, and there were some main culprits, we said, that you could focus on. What I've noted here is that the maximum amount of time it takes to rebuild is about 2.5 minutes there for glib. When we turned to Qt, the poor guys with the 2-hour-long build, we found that there were a lot of hotspots, 732 or so, but it was roughly 8% of the source code files, so on par with what we were seeing in glib. As far as main culprits, we started trying to manually analyze this stuff to find some main culprits, but it just 732 files was too much for us as outsiders looking in. We weren't really familiar with their system, so instead what we did is we found the components, or just the directories that had the highest hotspot concentrations. So these are like, of the files in that directory, how many of them did we find as hotspots? And some of them with really high percentages were the core library and the XML patterns one. But again, yeah, they had a really bad scenario where you could have files that were rebuilding very, very slowly. Then we turned to Postgres, and we found that only 2% of the files are actually hotspots here. So good job to those of you who are Postgres developers. Way to go. 27 hotspots, though. We still found 27 hotspots here. And in the worst case, it was just over 3 minutes to rebuild some of these hotspots. So some of the main culprits that we identified are here, these 5 files. So actually, if these 5 files were tackled internally, most of these hotspots would actually disappear. So if I kind of shift now to what we learned from doing all of these studies on hotspots, is that they kind of highlighted this transitive trend for hotspotness, if I could make up a term. So if we imagine that we have an object file that gets linked into a huge list of deliverables, a huge list of DLLs and executables, and this file changes frequently, we would flag it as a hotspot. So this C file here would be considered a hotspot. But if this C file actually ended up including a header file, this header file can actually, changing this header file can trigger the same amount of build activity. So it's going to end up having to recompile that object file, relink everything. And now if this header file also changes frequently, it's also going to be a hotspot. But that's not it. If this header file is also included in another header file, and that header file includes several other header files, and some of those are also hotspots, we've got what we call a super hotspot. So changing this file will actually trigger 3 hotspots to recompile, which then keeps getting compounded the further up you go. So the advice we have here is that you should try to limit the use of these header file hubs, so header files that just include other header files, because they tend to accumulate build activity, and if they change frequently, now these become hotspots. So just to quickly sum up what I've been talking about, so we started out saying what I meant by a build system. It's a set of order-dependent tasks that have to be executed in order to translate your source code and your documentation into something that your customers or your users need. And developers rely on the build system to be quick so that they can make their edits, change their deliverables, and test them quickly to keep that feedback loop fast. But there are some files that end up taking longer than others to rebuild, and they can really interfere with developers. So what we set out to do was come up with a way of finding these files so that you can refactor them and improve your build performance. So we first started out trying to find just the files that rebuild slowly. That didn't work out so well. We tried the files that changed the most often, which also didn't work out so well, but when they were combined, so we call these files build hotspots. And they're the ones that rebuild slowly, but also take a long, change very frequently. And we came up with an approach to find these files based on thresholds. Finally, we did some open source studies using our approach, found some hotspots, and found some general trends that we think could help avoid making build hotspots. So that's all I've got to say about build hotspots for now. I'd be happy to take questions from you guys, but at the same time, I'd like to remind you again that we put a survey up, and you can find it at my Twitter link. It would be really helpful to me, and we'd be happy to feedback the results to you guys if you could take the 5 minutes to fill out the survey. Thanks again for your attention. And, yeah.
Are there any questions for Shane? Ike,
Yeah,
please.
so I was wondering how you measured this. Were you using the parallel build, single process build things?
Yeah, this was just single process. But one of the things we want to look at is using this graph, we can actually find how Make would parallelize things, and we can actually find like problems that way.
My experience nowadays is that even if you have to compile everything, it's not so bad because parallelizes pretty well.
Oh, okay.
Depends.
Even when you're using recursive Make, have you had any problems with that?
Well, seems to be fast enough.
Oh, okay. Ah, cool.
It's, yeah, using, I mean, I know that recursive make it doesn't parallelize as well.
Oh, okay.
Otherwise, but it's good enough.
Thanks. I guess there's one other thing before we go into questions any further. So my supervisor, my PhD supervisor is here. He's at the back, and he's organizing a workshop on release engineering. So maybe he can tell you a couple of words about this thing.
Last year we had a workshop in San Francisco, the relevant workshop, which actually aimed not just at build systems, but at release engineering in general. So integration, version control, cloud, Puppet, and all these kind of things. This year we're doing it again because it was quite a big success. We had people from Google and LinkedIn, Netflix, also from open source there. This time will be hosted by Google in Mountain View. The deadline is February 28th. So you can send like a small abstract there, give it off. The event itself is 11th of April. We have already a TM speaker from Google, Dina over there, and there's another speaker coming. Big name. So anyway, so the deadline is still open, so feel free to submit.
So I have another question now.
Sure.
I was wondering, you have the quote about the GPK phone board. I was wondering, would there really be incremental builds so that the build gets changed?
I believe so. I believe, yeah.
That's interesting.
Yeah.
I think in our case, it's probably not so much the build for Postgres that's the issue. Because generally, even on a modern laptop, on a Mac like that with an SSD, Postgres would build in a couple of minutes,
Right.
usually.
Takes a while on my Raspberry Pi.
Yeah, we keep meaning to buy you something really quick. The bigger problem for us is actually, I would say, running the regression tests, because that takes orders of magnitude longer than actually building the code on those systems. For the GTK guys and the QT guys, yeah, I mean, I've built those packages myself, and yeah, they're horrendously slow.
Right. Yeah.
I can see how you could make a real difference to their daily work. Yeah, for us, I think it's, for me at least, it's more the regression test.
Okay. So your regression tests, are they smart enough to know only this stuff has changed, I should only run this subset, or do you just run the whole suite?
No, it runs the whole suite every time.
Yeah, cool.
There's workaround or attempted
Yeah, I mean,
100 else to do just the JSON.
Yes.
Really? Yeah.
I haven't really been following that thread. Within the company I work for, we have a vastly expanded regression test suite, and we have sort of subsets of it that we can run at any one time. But the main Postgres one, and I think it's just still the standard parallel and
Yeah.
serial schedules.
Yeah.
I mean, it's not too bad. It takes a few minutes on a laptop. There are more tests if you run all the isolation tests and stuff. Just take a little bit longer. Something like that.
How frequently do you run the tests? Do you run them after every change, or?
Well, we run automated builds for the installers that my team looks after, and we run regression tests as part of every build every night, and if we trigger a manual build. But for the Postgres project, we also run a website called buildfarm.postgresql.org, where we have lots of volunteers that provide time on their machines. So they run a small client that will do a git checkout, build the code, run the regression tests, and there's a couple of different ways we can run them. It runs the regression tests across the contrib modules as well, and then reports the results into the build farm website, so that we can see if anything is broken build on any particular platform. So I think we've got about 30 different animals at the moment. Different machines, architectures, compilers, combinations of them. And most of those are running at least one build daily. Probably in most cases they're running one build of each branch daily. But that's pretty distributed, of course. I mean, I'm running a couple of machines, Hayden's probably running his Raspberry Pi to death on it. So overall, none of us really see a huge problem with that. I guess the bigger problem is when the developers are running a regression test after making a change. It's time to relax and get a cup of coffee for 5 minutes or so.
Oh, okay.
So actually, that problem is quite common. So last year at that workshop, we had someone from Google came and had the same issue. The test took ages. So they also then started recording dependencies. So explicitly saying this test is actually testing this and this part, this component. Then they even had the dependency between tests. And then they could really nail it down. This thing changed. We don't definitely run.
Yeah.
It's an investment. It also depends how often we change the tests.
Yeah, I don't think with Postgres we're at anything like the stage where it would be worth us doing that right now. Certainly with the stuff that we run within the company I work for, we have some of our test suites on certain platforms can take close to 24 hours to run even on modern hardware. And that might be an interesting approach that we should look at.
I have a question. Can all this process be kind of summarized or automated in terms that you have a code branch and you just run through some kind of script or piece of software that can identify the hotspots? Is it kind of self-contained, so to say?
So at this stage, it's still a research prototype, which means it's not automated at all, and it's just me tweaking things. But yeah, it could very much be automated. The step that takes a while is the 10 clean rebuilds, just to make sure that we've got the right cost for each edge. But that's again a trade-off, right? You could build once and say that's the cost, and then every time you rebuild, you record again. But yes, essentially every step that I do manually right now could be done with a script or automatically.
Because there is always a risk that at some point somebody can include a couple of H libraries or something like that that could end up, and it would be very difficult to trace back when you have a community developing the software. So it's kind of would be useful to have like a tool that can actually go to the source at some stage and give a report on after every big change or every big release or something like that.
Yeah, that's interesting. Yeah, it could even be integrated with like a continuous integration server to make sure that every change we see what the impact is on hotspotness, to keep coining my same term.
Yeah, that would be very interesting. Like, so I remember Alvaro, one of the posters, actually spent some effort splitting up the header files a year ago. So I'm not sure if that's actually included in 9.2. So 9.3 might look different.
We did do it for 9.2.
Was it for 9.2?
The project does tend to do it every 2 or 3 years. Somebody will sit down and just clean up all the header files and remove unnecessary includes.
It's interesting to have a tool like this to see, when you do that, to see if you actually made any difference.
It would be nice to get that as a step in the build farm client.
And we should exchange emails. I can help you out with that, definitely. I guess I also, since I've still got some time, I had some bonus slides which name the... So I mentioned there were 5 kind of main culprits. These are the ones that through the chain of including, end up being hotspots because of that. So I don't know if any would jump out at you off the top of your head as being recently cleaned up. But yeah, so some 5 files get dragged in through the main Postgres file, through this htop details file. Each time I indent, it means another level of include. So yeah, you can see like this one's like 4 levels deep, but becomes a hotspot because it was included in files that were hotspots up the chain. Yeah, some more. So yeah.
So how do you do actually the splitting of header files? You have a tool for that? You look at unused header files or based on experience?
I think we have a tool that looks for unnecessary includes. But besides that, it's a manual process, as far as I know.
So, were there any other questions? And thanks again for inviting me to come out. This was an awesome opportunity. And one more time, there's a survey up there.
Thank you.
So the next session here will be at 5, and there will be the final, well, the announcement from Magnus, right?
Yeah. Did I get voted back in again or not? Did I get voted back in?
With elections results.
Yeah.
So thank you again, Shane.
Do you have any idea what you're going to coffee?
So I'd actually completely forgotten about it. I need to be here for the next session. If you want to run over and grab a please now, I can go right now.
Thanks for your
Even if you change it to heavy
So what just happened?
same thing. That's a whole.
Either way, but
But yeah, that test suite thing is
It'd be nice to publish. It'd be nice to have it published. Play with it.
the problem that I have is in the research world.
I know. Yeah.
Everything's that's a big idea.
Yeah.
Just hack something. If you guys think it would be useful,
So I take him, I believe he launched and reserve it on
Magnus did it, so
Let's get more of it.
things that are already
Alright, so I'll take a moment. I'll take over this down and introduce you.
Non è che è diventato un'azienda.
Get you for this.
Che sta lavorando per migliorare cose.
Because of my name or because of the do any development?
Allora hanno creato, cioè ora la polizia
Yeah. Why just got me
prodotto business intelligence
that they use now instead of contact.
intelligence, cioè noi abbiamo clienti, bravo,
And I'm working on add-on transactions.
poi c'è anche business
But
objects,
yeah,
funziona.
that Volvox from.
Noi arriviamo fino a
tendency to lose things.
I have a tendency to lose those things.
That's right. Yeah, so I'm like triple checking.
The amount of those I've left at home.
So what is it that you're?
noi si sta lavorando con un progetto
This I have to trade to get on. I have this universal adapter. It's a giant.
che sono le query di business intelligence. E poi c'è il progetto
testing because many companies run the same issue, lots of tests, and as soon as you do something you want to test, so what you do is you sure you test everything, which takes ages.
Yeah, it's it's been a lot more pronounced on certain platforms.
questo triennio
In particular, Solaris on Spark, we found has been very slow at running our regression suite. So you were just asking what I do for my company. So we're one of the Postgres support companies. We're probably the largest one. We also take so we sell support for community Postgres, but we take a copy of the code, fork it, and then add Oracle compatibility and various other features. So we sell that as Postgres Plus Advanced Server and support that obviously, as well as supporting Postgres, and obviously contributing to the community and providing installers free of charge for people, that sort of thing. So our regression test suite for just the core database server for advanced servers is based on the same framework as Postgres is. But where Postgres has got a few hundred tests in it, ours has got a few thousand, because we don't have the benefit of all the community looking at our Oracle compatibility code, so we test the crap out of it, basically. And yeah, we found that suite, there are certain things that we've not got to the point where we've invested a lot of time in trying to track down just yet, but we know there are hotspots in there which on Solaris Spark in particular seem to be very slow, even on very expensive test machines. I don't mean expensive like a production server for a big website would be, a sort of build and test machine that costs 40,000 or something. It's fairly pricey. And we can, on a £40,000 Spark machine, have a regression test suite that takes 24 hours to run, that on Linux will run in 8 hours.
Right.
And it's some pretty bizarre.
Some disk I/O related or so?
Yeah, like I say, it hasn't caused us enough problems yet that we've dived in that deeply. I mean, we've done some basic instrumentation and narrowed it down to a few particular tests, but haven't actually come up with any real clues as to what the common factors are, if there are any, that kind of thing. It's just,
that's a huge
seems to not be particularly efficient on that workload for some reason.
Well, I never know. Of course, if you have customers using that platform, then
we have customers using the platform, but they don't seem to run into any problems with it on production workloads. Because the regression test framework does a lot of things that you wouldn't necessarily do on a normal production system, because it's doing different loads and things to try and set up databases for tests that you're about to run, that sort of thing. Which it's very random compared to what you might be running on an actual production system that's just doing the same thing, running the same web app or ERP system all the time. Yeah, it's an interesting idea that sooner or later we're going to get to the point where our regression test suite is, even on the platforms where we don't have these problems, it's just going to take much longer to run than we want it to. Yeah, I never considered thinking about dependencies between the tests and the changes.
The thing, of course, like you can have dependencies, but then of course you need to maintain them as well. So you need to some way which it's, because if you like a tester adds a new test file, some test script, and he has to figure out where he needs to put dependency, that slows him down, and then so you can have repercussions.
Yeah, that would actually be kind of difficult for us, because it's the QA team that would actually develop tests based on bugs and feature requests that have gone in. But those guys wouldn't have any knowledge about how a particular feature was actually implemented. So they wouldn't. I imagine that would be quite a common problem in a software house where different sets of people doing the development to the actual
Yes, you can leverage like a dependency graph to kind of automatically have them, and then you say based on their includes or something. Kind of.
I'm not sure how you'd figure out a direct relationship between it programmatically, because we wouldn't want to exclude things like, for example, if you created a new test that was to test a specific aggregate that we'd added to the database server, you could very easily link that test and say, well, only run this test if these 3 source files which implement that aggregate function they've changed. But actually, we tend to want to do more than that. We still want to be. We would want that test to be dependent on any other code paths that may have changed in the database. You know, things that might call the aggregate function, bits of the planner that might figure out how to use differently within a query path. And I imagine that might get quite tricky to do.
Yeah.
Profiling tools might help there. If you profile while running the test, you can see which functions are called.
That's an interesting idea. Run it a few times in different scenarios and see if you get some fairly stable results. Start to take that as being a pretty good indicator of what matters. Well, I've seen 3-4 talks today, and I can honestly say this one's given me the most to think about.
Cool. Yeah. Thanks for sticking around. I'm really thinking about popping out. Yeah.
Good, thank you. Topic I've never seen at PostgreSQL. So I was a little nervous when we chose your talk, but it paid off.
Cool. Thanks.
Anyway.
So, do you have time to pop down now, or is it too late?
So Vic said he was going to wander down with you. I didn't really want. Yeah, he's right there. He's going to take some things back to the booth anyway. He knows where everything is.
Cool.
Yeah, we've got our election results, and I was standing for re-election, so I really want to be.
Good luck.
Well, there was only 3 of us running for 3 places, so I think it's a full because I still probably should be there anyway.
Yeah. Congratulations. Congratulations. Thanks again.
It's just that.
This one. Okay.
It's a South American energy drink.
It's German and then to drink.
Yeah, that's exactly what I meant. See, I asked this same question about 2 hours ago.
They have this.
We brought the elephant. Took a while. It's on his way. There he is.
Where is he? Yeah.
That's a quicker pause at the MySQL booth. It's hardly welcomed by the Python. No, it's Slavic. It doesn't look by definition particularly evil. That's okay. I'll guarantee you that I will not run over time for 45 minutes for this.
You sure?
Yes.
So I thought that was an interesting talk. Like I said, I'm not sure it's that relevant to us now. The approach they were taking.
I mean, there were no surprises in the list of files.
Even when Did you get lost?
No, it didn't.
Everyone's here.
Well, I assume Maya's
Yeah, Maya is there and Peter is there.
Yeah. But I was just saying, who won?
Yeah, so am I.
You think it'll take 40 minutes?
No. It might take 10.
We don't start for 10.
I'll get. Oh, what? Everyone's here.
Everyone's not here.
Oh, we have to wait. We have to wait 11 minutes.
Yeah.
Just
Well, I mean, previous sessions haven't actually finished yet.
no, on paper. No.
Reminder from the FOSDEM app to go to this talk. Okay, that's good to know.
You're gonna
Especially when you give it. No?
want that last bottle of water, Magnus.
Yes. Thanks for pointing out that there was a bottle of water there. If you just grabbed it, I was kind of better.
No, it's sort of low, but
Well, there's no like mugs or glasses or anything. So I could pour some over in there. But
It's already in a semi-block.
yeah, but for him. You'll have I'm not actually planning to present anything either. You just want to charge?
You do not need this charger?
No.
Catering is looking for excuses.
And did you find?
Of course you find some lame excuses.
Das war schon nah am Kaffee da oben. Nur ein bisschen süß und ein bisschen hell.
FOSDEM schedule doesn't work. What's an Epi4 experience?
How not to do it?
I tried and all the services I'm using don't work.
I didn't even notice they only had a V6 because everything just worked.
Not for me. I had to switch. As I said,
What services were you using?
quite a shitty website.
Yes, quite obviously.
They ran out of IPv4 and
I've been tracking payments we're making, and then right in the middle, this moment I signed up for the Postgres Europe membership. My first reaction was, how did we get the email address out of the card machine? Turns out to use the website.
what do we call these?
Bugs,
Bugs.
apparently. Elephant bugs. Not Postgres bugs, because Postgres doesn't have bugs. Christoph told us that.
Yeah, except 1 or 2 bugs in the application. Still big guy. Das bug is like another guy has to work with this.
But none of that was in stuff I did.
No.
This time.
So we were actually distributing bugs to them?
Yeah.
What's wrong with this picture?
Yeah, we couldn't fit the Trojan horses.
Let's start.
There's 1 minute left.
Be strict on time.
Let me
People might be timing it, and right
me
at the right minute, like
sync my
400
clock.
people just.
I'm timing it.
Let me sync.
I don't care about you.
In a minute and a half, it's not.
No, it's less than that.
Ah,
It's less than a minute. I'm waiting for Slonic.
well, I have a resolution.
You were supposed to stand in that corner and dance the whole time. We agreed on this.
Better on clock size, it's 5 o'clock.
Yeah.
Go ahead.